Good afternoon and welcome to the Smithsonian National Air and Space Museum here on the National Mall in Washington, D.C. My name is Matthew Schindel. I'm Curator of Planetary Science here in the museum in the Space History Department. And we're here today in our Moving Beyond Earth gallery, a gallery that celebrates human exploration into Earth orbit and beyond. The folks that we're going to hear from today have never left the Earth, but they've nonetheless explored the outer solar system and in a sense have been our human representatives out in space to the outer planets. And we're here today to celebrate and commemorate with them the 40th anniversary of the Voyager spacecraft. It was an epic mission to explore the outer planets, a mission that to this day I think stands out as one of the most ambitious that NASA ever sent out into the solar system. To me, the mission has personal relevance, not because I was ever involved with it, but because as a child, the encounters with the various planets, actually the two final planets, Uranus and Neptune, helped to define my childhood and also helped to define my own understanding of our place in the solar system. I was too young to enjoy the flybys of Jupiter and of Saturn, but Uranus and Neptune I remember quite clearly as a kid seeing the images on the news in the evening news and just really being impressed by what we were doing out there in the solar system, that I could feel that I was one of the first to see these planets in such great resolution. And I'm sure that several others of you who, like myself, perhaps were born in the 70s might feel the same way. And also, I want to note before going any further that we do have a wonderful model of the Voyager spacecraft upstairs in our Exploring the Planets gallery that is, true to the actual Voyager. It's built from some of the parts that were used in engineering and testing the Voyager. And if you want to see that spacecraft in its real full size and glory, I suggest that you take some time, if you're here in our audience, to go upstairs and take a look at the model. And if you're not, if you're watching us on NASA TV, please come to the museum when you can and take a look at that model. I don't think you'll be disappointed. So to get started, I'd like to introduce Dr. Thomas Zurbuchen. He is the Associate Administrator for the Science Mission Directorate at NASA and is headquartered here at NASA headquarters in Washington, D.C. During his career, Dr. Zurbuchen has authored or co-authored more than 200 articles in refereed journals on solar and heliospherical phenomena. He's been involved with several NASA science missions, including Ulysses, the Messenger spacecraft to Mercury, and the Advanced Composition Explorer. So, Dr. Zurbuchen.
Well, thanks, everybody. It's really a pleasure to be here with you today to celebrate this pioneering moment for both NASA and for exploration history of humanity. Happy anniversary to Voyager. Yes. Of course, you know that on September 5th, 4 decades ago, in 1977, NASA launched the Voyager 1 spacecraft, only a little over 8 years after the blast-off to Apollo 11 in 1969. In exploration terms, Voyager was and still is, to me and to so many, the Apollo 11 of space science. It's a mission that changed everything. It not only changed what we know, but how we think. It's about exploration of the unknown and redefining what we can and cannot do as humans. Imagine this fall, children all around the region, around the country going to school, getting their school books and looking at these pictures in these books and looking at especially the pictures of the planets. Many of these pictures, of course, are pretty young. Mercury has pretty cool pictures. I know, because I was on the Messenger mission, as you just heard, taking images there. You go look at Mars images, some of the most amazing investigations going on right now, both on the surface and in orbit. But then you go farther out, and all of a sudden you get to Neptune and Uranus. And frankly, Every picture you see there at high resolution comes from these spacecraft that are out there, from the spacecraft that flew by, that are out there, and we have not gone back. To me, it's also the beginning of my interest in space science. The first book I ever got, under the Christmas tree for me, just when I was a little bit under 10 years old, was to celebrate the upcoming launch of Voyager, the first Voyager, Voyager 2. And I had this book with me, and it's still in my office. If you visit me at headquarters, come look at my Voyager book. For me, it was an inspiration. We all, is my point, have a personal story that relates to Voyager, even if we were not fortunate enough to be there with hands-on, like so many of the people we're going to hear about. So Voyager today affects the lives of children of all ages, all over the world. No, the children were not born that are going to school right now when Voyager was still on the ground. Well, not even their parents were born for many of them. Half humanity that lives today was not born when Voyager was launched. And so really what we're celebrating today is 40 years of discovery and exploration, history eclipsing everybody's expectations. Nearly 40 years later, the successful Voyager 1 and its sister spacecraft Voyager 2 continued to provide us with unprecedented information about the place in space we live in. Voyager 1 has now traveled more than 13 billion miles from Earth, the farthest than any spacecraft. It's now traveling through the emptiness and loneliness of interstellar space, having left the sphere of influence of the sun. It's expected to transmit data until about 2025, if none of the essential technologies fail. Voyager 2 is approaching the boundary of the heliosphere. It's just mind-boggling, still going. As I said, Voyager is the Apollo 11 of a robotic exploration, a robotic explorer to the space beyond and beyond the imaginable. It is a mission driven by scientific research and enabled by innovative technologies, a mission of pioneering and inspiration. It's a mission that has opened entirely new questions that keep us awake at night today. They're questions that are subject of ongoing science investigations. Cassini, in its last orbits, is hard to imagine without Voyager ahead of it. The images of Saturn rings are all over monitors today, on my phone as well. And we think of Enceladus and its ejection of water from below this icy surface, again, starting with Voyager. Every 50 days or so, we look at new images from Juno. I just talked to a co-investigator on the mission. And, of course, remember Galileo. One of the most recent passes of Juno went over Jupiter's gigantic storm, which has lasted for millennia, getting weaker. And we are imagining the next missions to explore Europa, one of Jupiter's moons, which harbors great surprises, we believe, below the icy and cracked crust. A whole ocean of wonders that remain to be explored. In fact, we just put an announcement out to the science community to make the next step towards understanding the boundary of that sphere of influence of the sun, the heliosphere. And this mission, IMAP, as we call it, is to map out this giant acceleration region out there and also detect interstellar gas at ways we've never seen before. Again, a research topic started with Voyager. Because guess what? We're dreaming even bigger. These technologies that we have today allow us to go to Voyager distance, but we want to go farther. We want to go faster. And we're inventing these technologies because we're dreaming, of course, together with the children of this world, about possibly traveling sometime to other stars. That's the direction Voyager has pushed us in. So I want to congratulate to all the generations of the Voyager team. Remember, of course, the ones that are no longer with us. And we celebrate the ones who are making Voyager work today, from NASA JPL all the way to Australia, where a big satellite dish listens to Voyager in the deep sky. Congratulations and encouragement to those who are squeezing every ounce of science out of these bits, these rare and precious bits that are coming from deep space to us. So I want to thank Suzanne Dodd, the current Voyager project manager, who first began working on this mission in 1984, and Suzanne told me that many of her friends are here. I know Andrea, of course, I worked with her, are here, and I'm just so excited to welcome you all from JPL who are, many of you have started in the 80s, some of you have started more recently, and we won't say who, but I'm just really excited that you're here and celebrating with us. Dr. Ed Stone is my friend for decades, the retired director of NASA's Jet Propulsion Laboratory, and on the Voyager project team since 1972, a major spokesperson for the Voyager science team and one of the key contributors to the science. Andrian co-wrote 6 New York Times bestsellers with Carl Sagan. It's still inspiring to me. I keep going back to these, so thanks for all the work that you've done. A creative director of NASA's Voyager's Interstellar Message Project, including music and images. You're going to talk to us about it. Gary Flandreau, who conceived, the innovator here, who conceived the Planet Grand Tour multi-planet mission using the gravity assist technique to reduce the mission duration from 40 years to less than 10 years. NASA used this, of course, with Voyager 1 and Voyager 2 missions. And Dr. Alan Cummings, another friend for many years, and as I often said, one of the funniest guys in any party you will ever go to. Look at him when he's up there. You'll know what I mean. A senior scientist, a Caltech physicist who works with Ed Stone, studying the nature of particles entering the solar system from the local interstellar medium and also locally accelerated. Glad to have you here as well. And I want to thank the National Air and Space Museum for hosting us. It's a lovely place. Since I moved to town, I'm here more often than I care to, tell you right now. I'm coming here with my children or by myself. You all perform a remarkable service every day, educating and inspiring the public of all ages. Let these lonely spacecraft be our inspiration and drive us to keep pushing against the walls of ignorance to be researchers, explorers, and in fact, voyagers. With that, what I'd like to do is kick off a movie that was prepared for this event. Thank you so much.
40 years ago, NASA sent 2 spacecraft on a grand tour of the planets in our solar system. Voyager 1 and Voyager 2 were built to explore and to carry a message to potential spacefaring civilizations. Like a time capsule, the Golden Record carries a message about Earth.
We had 6 months to make the Voyager record, and we wanted everything we could possibly compress into the space allotted on the record, as well as the sounds of Earth. The idea of making a record that would represent the entire planet.
The Golden Record contains music, 115 images to showcase our home planet, and greetings in 55 languages.
Tanti auguri e saluti. Bonjour tout le monde.
Hello from the children of planet Earth.
We wanted to convey something of the joy of being alive.
The Golden Record is expected to last nearly 5 billion years.
We knew that the spacecraft itself would speak volumes about us, as much perhaps as the message and more, which I might add has exceeded its design specifications in every conceivable way. This was a spacecraft that was supposed to function for something like 12 years. Here we are 40 years later, and we're still in touch. And look at the discoveries that both Voyagers have given us, including, most recently, the borderline of the heliopause, that place where the wind from the sun ends and the interstellar medium begins. NASA has every reason to feel the utmost pride.
Both Voyagers are still traveling, more than 35,000 miles per hour, carrying our message to the universe.
It's now my pleasure to introduce our first panel of the day. Dr. Zurbuchen actually already gave them all pretty good introductions. Allow me just to briefly reintroduce them. We have Dr. Ed Stone, who has been a project scientist on Voyager from 1972 to the present. We have Dr. Gary Flandreau, who is the Boiling Chair of Excellence in Space Propulsion at the University of Tennessee Space Institute, and who was the first to sort of propose the Grand Tour multi-planet exploration of the outer planets. We have Alan Cummings. Alan Cummings is been employed at the Space Radiation Laboratory of Caltech since 1973, and he is presently a current senior scientist and member of the professional staff there. We have Suzanne Dodd. Suzanne Dodd is JPL's director for the Interplanetary Network Directorate, and she has over 30 years of experience in spacecraft operations, serving as project manager role in Voyager and also other missions. And we have Ann Druyan. Ann is an author and lecturer and television and motion picture writer-producer, whose work is largely concerned with the effects of science and technology on our civilization. She was co-writer of the Emmy and Peabody Award-winning television series Cosmos, and she served as creative director of the NASA Voyager Interstellar Message Project. So without further ado, I will start asking our panelists a few questions to talk about the Voyager mission. We'll start with Dr. Stone. So Dr. Stone, to you, what is so special about Voyager?
Well, from many points of view, Voyager really represents humanity's most ambitious journey of discovery, and that's what really I think is its legacy.
And tell us about the beginnings of the mission, the early years.
Voyager began when Gary Flandreau, who you'll hear from in a few minutes, discovered that there was a year 1997, plus or minus a year, where a single spacecraft could be launched. It could fly by all 4 giant planets. It was called the Grand Tour. That was in 1965. By 1972, they had been sort of downsized to MJS-77, which is Mariner, Jupiter, Saturn, 4-year mission just to those 2 giant planets and their moons and rings. That fortunately was to be launched in 1977, however, so that if they continued to work, they could go on to Uranus and then finally Neptune, which is what Voyager 2 did, completing the Grand Tour of the outer planets, as Gary had promised a way to do that in 12 years rather than 30 years. So we really have him to thank that we could do it in a 12-year journey.
Voyager obviously has made many discoveries. What are some of your favorites?
Well, if I could have the first slide, please, which shows Jupiter and its great red spot, along with 2 of Jupiter's moons, Io and Europa. Before Voyager, the only known active volcanoes in the solar system, if I could have the first slide, please. No slides. The only known active volcanoes in the solar system were here on Earth. And then Voyager flew by Io, a moon of Jupiter, about the size of our moon, but 10 times the volcanic activity of the Earth. Quite a striking change to realize the Earth was no longer the most volcanically active body. Before Earth, the only known liquid water oceans were here on Earth. And then Voyager flew by another Jupiter's moon called Europa. It was covered with ice, and Voyager saw it was cracked ice, as though it were an ice over a liquid water ocean, which the Galileo mission subsequently demonstrated was indeed the fact. There is a liquid water ocean. You see the 2 moons in this image, Io being the orangish colored one because of the volcanic activity, and Europa being the white one because of the ice pack, the icy crust. On to Saturn, one of the key issues there was its moon Titan. Before Voyager, the only known nitrogen atmosphere in the solar system was here on Earth. And then we flew by Titan, which is the fuzzy ball you see here, which has 50% higher pressure nitrogen atmosphere than here on Earth, but has methane, natural gas, in the atmosphere, not oxygen. And so the action of sunlight is to create complex organic molecules which create this haze that cannot be seen through in the visible. Fortunately, the Cassini mission appeared several decades later with a radar system that could look through the clouds, through the haze, and saw that indeed there are lakes of liquid methane, liquid natural gas on this moon, perhaps resembling what the early Earth may have looked like before life evolved. On to Uranus. Before Voyager, all the known magnetic fields all had their north poles and south poles oriented to be near the rotational axis of the planet, because presumably it was that planet rotation which created the magnetic field. And then at Uranus and then at Neptune, we found the magnetic pole was actually nearer the equator than the pole. Suddenly, our terracentric view from Earth of what magnetic fields were like had to be greatly expanded. The final object we visited in the solar system was another moon, a moon of Neptune called Triton. It's smaller than our moon. It's much colder, 390 degrees below Fahrenheit, and so cold that the nitrogen is frozen into an icy polar cap that you see. The white polar cap in the south is nitrogen ice, but the dark streaks are geysers erupting and depositing on, and we found 2 active geysers at the time we flew by on a world that is so cold that even the nitrogen is frozen. So Voyager, time and time again, caused us to greatly expand what we thought we knew about planets, what we thought we knew about rings, what we thought we knew about magnetic fields, what we thought we knew about moons. It's just changed and created a legacy of discovery now for many future missions to the outer planets.
So, Dr. Flandreau, I'll ask you a question next. So how did this mission end up being possible in the span of only a dozen years?
Well, the key here is to use free energy that you can. It's not using rockets now. We're using some free energy, which I will explain. Let's put the first slide up. I can use that, I think, to show. First slide. Okay. This is actually the result of thousands of calculations. I've had to run thousands and thousands of numerical calculations of trajectories looking for the possible outer planet mission. This was my favorite here, and the first one that was published, showing a 1978 launch from the Earth. I put this up so that you can get some idea about the angles that you have to deflect the trajectory through to gain energy, by the way. So I start from the Earth here in September 1978 on that little tiny dot along that dashed line, make a 135-degree turn over to Jupiter, and here's now where we start gaining energy. If I didn't do anything, if I didn't go past Jupiter, I would come right back to the Earth, basically, on an ellipse. But now when I go past Jupiter, I get a tremendous slingshot effect. Jupiter is moving along and it's pulling us with its gravity field. We sometimes call that gravity assist. Adds a tremendous boost of energy. I used to like to tell my students that if I took a spacecraft the size of the Voyager, or about a Volkswagen size, that's equivalent to about 4 Saturn V rockets waiting for you out there. If you could hook those up, you can really get a tremendous boost in speed. Now it's never going to come back. We've lost the spacecraft. It's on a hyperbolic orbit now. Heads over there to Saturn. You're going to ask me in a minute, where did I figure this out? I'll show you. Anyway, we get to Saturn, and in this one, in 1978, I loved this one because I could get so fast. I would get clear out to Neptune in about 7.5 years. To do it, you'll see with Saturn, see the little rings there, I had to go between the planet and the rings, okay? That scares people. Although Cassini's been doing that now recently, okay? And you get a huge boost, and you can get then to Uranus really quickly, and then on to Neptune. And then we're on the way out of the solar system. That's where we go interstellar at that point. But the interesting thing here, and by the way, here I am doing these things. I say, how could we ever sell this? But the key to selling it is to notice that some important event happens within 4-year time spans. If it doesn't, then you're never going to get any money from the government, right? So anyway, that's what made it work. And let me show you how we found it. Let's go on to the next slide, please. The next slide shows the actual thing that I used to figure out that you could do it. Along the bottom are the dates. I was looking for the next 10 or 20 years from when I was working in 1965. On the top, or on the other axis, vertical axis, these are the angles I was showing you in that last slide. And I could see something really remarkable here, that in the later 1980s or so, all of the tracks of the outer planets crossed so that the planets were all on the same side of the sun. We said, oh my gosh, I better look there, because that means you could probably get one spacecraft that could hit all of those planets, which is what happened. And that's how it was discovered. And then now the hard work starts. You have to run all these trajectories until you find the best launch windows. Let me tell you the answer there was 1977, 1978. And the real problem here is that only recurs every 175 years. So if you miss this one, you've lost it because it takes time, to build a spacecraft. We had about 10 years to do it. And the last time this opportunity ever came was when Thomas Jefferson was president, and he muffed it. He lost it.
So you've already anticipated one of the other questions, but let me ask you, the first successful gravity assist was 1974 with Mariner 10. So how did you know that this would work, or what other problems did you think might happen?
I knew it would work because astronomers have known about it since the 1700s. And a lot of people since then have known that if you just fly past a planet, you will gain or lose energy depending on which way you pass. So I knew it would work. Everybody knew it would work. We demonstrated that also with the Mariner Earth, Venus, Mercury trajectories and so on. So yes, we knew it would work, no problem. Just getting money to do it was the hard part.
Well, I won't ask you about how you did that then. But we'll move on to Alan Cummings. Dr. Cummings, tell us how you first got involved in Voyager.
Okay, well actually I got involved with Voyager because I lost the experiment I had been working on. It went missing in action, seriously. What happened was I was up in Fort Churchill, Canada in 1973, the summer of '73. And I was doing what we had been doing for years, which was attach our experiment to the bottom of a huge balloon, send it to the top of the atmosphere, and where we took our measurements. And the idea was it drifts west about 500 miles during the course of a day. Then you cut it down, you bring it down, you recover it, and you bring it back and you start all over again. But this particular time, and I think this is the only time in history this has ever happened, the command to cut it down didn't work, and the backup cut down timer didn't work, so it just kept going. It went right around the world. It went around the world twice, actually 1.5 times, because the second time over Russia, they noticed it and they got it. And so that ended that experiment. And I got back to Caltech, all dejected, and they said, well, how would you like to start working on a new project called MJS 77, which was the early name for Voyager? And I said, okay. And the rest is history. I've been working on it ever since. And now looking back on 1973 and losing that balloon, it wasn't all that bad. I mean, I got to start working on the greatest mission ever, really.
So you were put in the right place at the right time with idle hands.
Yes.
Yeah. So tell me about your experiences with Voyager. What are some of your memories of it?
Okay, well, right off the bat, one of the early ones was that I think I was the last person to physically touch the spacecraft. Right during the last step of encapsulation of the spacecraft, we were worried about our fragile windows on our instruments. So I was allowed to crawl up in there, climb up in there and inspect them. And part of the inspection process was to make sure that the little windows were tight on the telescopes. So I gave each one a little twist. So it is eerie to think if I was the last person to touch them, the next person to touch them is going to be a space alien. The other thing, and bring up this slide here, yes. This is a picture of our cosmic ray team looking at our first data in 1977 from Voyager 2. And I'm the one, by the way, in the front there bent over.
I could tell. I could tell from the rear end there.
I was the only one apparently that could read the data upside down. But it looks like at the time this picture was taken, we were not completely convinced this instrument was working. But it was, and it has been ever since for 40 years in space. But for me, I'm a cosmic ray physicist, so getting Voyager 1 into interstellar space was sort of the holy grail in my area of research. That's the first time you can measure the low energy part of the cosmic ray distribution. Due to solar activity, those particles are not detectable inside the heliosphere, so you can only do it when you get there. And now we're there and we've measured it. And that's important for a lot of different reasons, but one is that galactic cosmic rays are a hazard to astronauts on long duration missions. And now we know that the sun goes quiet for an extended period. What is the maximum intensity of cosmic rays that the astronauts would have to deal with?
Let me ask you a question. Maybe you can explain to us, how do we know that Voyager is out in interstellar space?
Okay, so that took quite a while to sort out, actually. From our cosmic ray data, we said immediately, the way they behave, we said, okay, yes, we just entered interstellar space on August 25th, 2012. But then the magnetometer people came along and said, but you know, the magnetic field direction didn't change at all. So that would mean that the sun's magnetic field and the galaxy's magnetic field were lined up. And that didn't seem likely. So then the plasma wave team came to the rescue. And that's, I'm going to show it here in a minute. But anyway, the sun sent out some big blast waves, had sent out some big blast waves, and they reached the vicinity of Voyager 1, and it caused the plasma to oscillate. And the plasma wave experiment measures the frequency of those oscillations. And it turns out if you know the frequency of those oscillations, then you know the density of the plasma. And that's shown here. These colored splotches represent detections of the oscillations. And it turns out the density that is inferred is the density expected in interstellar space and not inside the heliopause. So that's when we knew that Voyager 1 had gone interstellar. And by the way, modelers and theorists are coming to grips with the magnetometer data and figuring out that why that happened. And it's just the interaction between the heliosphere and interstellar medium is a little more complicated than we first thought.
Well, Dr. Dodd, you're currently managing the Voyager interstellar mission, so maybe we can start by asking you, where exactly are Voyager 1 and Voyager 2?
I like to say that the joy of having two spacecraft is as Alan was saying, you have to have a model that fits both data points. So we have two spacecraft, they're identical. Voyager 1 is the one that, if you look on this graphic, it's sort of going up and out toward the nose. It's in interstellar space as of August 25th, 2012. Voyager 2 is going down and out of the plane of the planet. It has yet to cross the boundary into interstellar space. That's probably the #1 question that anybody that works on the project gets, but I always defer that question to Dr. Stone. So Voyager 1 was actually launched second, but it is traveling the fastest. It's the furthest spacecraft from us at 13 billion miles. It travels at 38,000 miles per hour approximately. Nothing's going to catch up to it. And Voyager 2 is traveling a little bit slower, 34,000 miles per hour approximately, but that's still 40 times the speed of sound here on Earth.
So moving that fast and being so far away, how do we communicate with these spacecraft?
Okay, well, because the Voyagers are so far away, they need to use the Deep Space Network antennas, which are the very, very large array dishes. They're 70-meter antennas as well as 34-meter antennas, and they're located in Australia and in Spain and here in California, or I'm not in California now, my apologies, back at my home in California. And so the way Voyager operates is slightly different than other missions in the sense that most of the data comes down continuously in real time, set down to the Earth, and we capture the data with the Deep Space Network antennas. So when we're listening to that data, we capture the data, and we capture data from both spacecraft about 4 to 6 hours a day from each spacecraft. We send commands to the spacecraft approximately once a week. A lot of times those commands are just, how are you doing? Now, because of the distance, the round-trip light time for Voyager 1 is 38 hours. So what that means is us as engineers, we're in our office on a Monday afternoon, we type a command that says hello to Voyager, send it off. We come back into the office, not Tuesday, but Wednesday morning, and Voyager says, I'm fine, how are you doing? So it's more than a day and a half round-trip flight time for Voyager 1. And that has its own challenges in communicating with the spacecraft.
And how are the Voyagers doing?
Well, pull up the next slide. And the Voyagers are healthy, and as healthy as senior citizens can be. That's the way I like to think of them. They're twin spacecraft, identical, and think of them as twin sisters, senior citizen sisters. So each has had different ailments over the years. For example, Voyager 2 is tone deaf. Every time we send a command to the spacecraft, we have to put it in a few different frequencies in order for the spacecraft to hear it. Voyager 1 does not have an active, an operating plasma science instrument. And what that means is that Voyager 1 cannot really directly feel the solar wind and the high energy charged particles coming from the sun. As Alan explained, it sort of had to infer that from a different instrument. So each of the spacecrafts had redundant subsystems when they were launched, and over time, certain things have broken. We've had to go to the backup systems. We've also turned things off. Power is our limiting resource. We use radioisotope thermoelectric generators on Voyager. They're the big canister booms out here on the left side of the image you're seeing. And we lose 4 watts of power a year. So now, especially going into our 5th decade of operations, the real key is how long to make this spacecraft operate, and when will we have to start turning off instruments, and how long can we last? And it's a balance between the engineering and the science desires. And we hope to keep this mission operating, have science instruments operating at least one into 2025. It might be a little bit longer, 2026, 2027, we're not sure. But personally, I hope that I can sit here 10 years from now with all these folks and talk about the 50th anniversary of Voyager launch and still have them flying.
Well, Anne, the golden record is probably one of the most well-known objects in the history of space exploration. What can you tell us about it that maybe we don't already know?
Well, a lot of people think that it was just the whim of Carl Sagan and 1 or 2 other people, but in fact, we consulted ethnomusicologists all over the world who haven't really gotten their just due in terms of the beautiful music that they brought to us. Many people have said in the decades since that the Voyager record is kind of the beginning of world music. And that was very much due to Carl's planetary perspective and our desire not just to represent the imperial culture that had created the spacecraft, but also all of the different ways that we found to express the joy of being alive. And so I found something out about the Voyager record 2 days ago that I never knew in all these 40 years. And that was, there's a Peruvian wedding song, which is sung by a child in the Andes who was recorded by a wonderful ethnomusicologist named John Cohen. And we had never thought to ask what the words in Quechua mean. We just knew it was a wedding song. And we just found out that it is a scathing indictment of the male chauvinism of that culture and the nightmare of being a powerless woman in that society, which came as a complete revelation to me. So, I think there are so many revelations hidden deep within the 27 pieces of music, the sound essay, the greetings from the humans and the humpback whales. There's a lot to learn.
Well, it sounds like it's been very meaningful for you. You've found a lot of meaning in the record. Have you imagined what it would actually sort of say about humans to a totally alien species if they discovered it?
Virtually every single night of my life, I've imagined. I stare at, I'm lucky enough to have that beautiful golden cover etched with the scientific hieroglyphics. And I stare at it and I've imagined on countless nights, because it's real. They really are moving between 35 and 40,000 miles an hour. They are as real as we are. And so to try to imagine traveling alongside these spacecraft and then to think that the design specifications, that Voyager has exceeded NASA's fondest, craziest dreams for it. And so when they say, the record's going to last for 1 to 5 billion years, I say, here we are 40 years later. It could be even more than that. Space is very empty. The chances are very small of it being intercepted, of either of them being intercepted. but I have imagined countless times, some grad student on some interstellar steamer who has a whole, collection of these artifacts from these adolescent technological civilizations that just can't wait to tell the cosmos what they can do. And, popping it on the stylus, which we included, listening to it, and maybe rocking out to Johnny Be Good and thinking, wow, these guys, they knew how to party.
That sounds like the basis for a great book. We now have time for a couple of audience questions. Yes.
Hi, I'm Emily Farfara from NASA's social media. We have a lot of questions on social. This first one comes from Twitter, and it's from Ms. Druyan. Can you elaborate on your brainwave EEG that's inscribed on the golden disc and the love story inside?
Oh, with joy. I would be happy to talk about that. So while we were at the Voyager record at CBS Studios in Manhattan, one day I asked Carl if it was possible if I were to meditate and all of the impulses that my body was giving off, my EKG, my EEG, every, REM, every single thing. Was it conceivable that the extraterrestrials of a distant time could reconstitute this meditation and interpret it? And I remember Carl's beaming at me and saying, a billion years is a long time, Annie, go do it. So I went to NYU Medical Center, was hooked up to a computer, which was the size of a vast room, probably much more feeble computing power than in our iPhones. And I was blindfolded and sensorily deprived, and I meditated for an hour about the history of the planet, its geology, its biology, its emerging technology, to the best of my very limited abilities. Told the story of our species, history of our civilization since the invention of agriculture. But this was also just a few days after Carl Sagan and I realized how deeply in love we were and had told each other on June 1st, 1977, in the throes of this mythic undertaking to speak for Earth for billions of years. And so part of my meditation is the joy of a 27-year-old woman madly in love, truly in love, as every single heartbeat since that moment can affirm. So that's on Voyager, and if that can be interpreted, then in some sense it keeps us all alive and the deepest feelings and the greatest joys we've ever known.
We have one more question.
One more question from social. Do you think Voyager 2 will reach the heliopause before its nuclear power batteries are exhausted?
That's Ed's question.
Will it reach the heliopause before the batteries go on?
Oh, well, Voyager 2, yes, we certainly expect so. We don't know, of course, this is exploration, but it's of several more years, but of that order, not 10 more years. So if we don't reach it in 10 years, that will be a very big surprise.
Okay, well, we have a second panel coming up that's going to be a couple of younger scientists whose lives and careers have been impacted by Voyager. But first, we have something we think you're going to find very cool. We're going to throw things over to JPL, to Mission Control for the Voyager Interstellar mission. And there we have Tracy Drain to explain what's going to happen. So, Tracy?
Thanks. I'm Tracy Drain, the Deputy Chief Engineer for the Juno mission, managed by NASA's Jet Propulsion Laboratory here in Pasadena, California. This is Mission Control for the Deep Space Network. This is where spacecraft from all over the solar system and beyond communicate with the Earth through a set of large antennae distributed around the world in what we call the Deep Space Network. The Voyagers have been communicating with us this way for 4 decades. And in fact, we're in a communication pass with Voyager 1 today. You can see on this live screen behind me that we're talking to Voyager 1 with station 63. In celebration of 40 years of continuing exploration with the Voyagers, we launched a campaign called Message to Voyager, which was inspired by the uplifting messages on Voyager's golden records. So we asked you to submit messages of goodwill that we took and selected the top ones and put out to a vote. These had to be short missions, short messages, no more than 60 characters. So we're going to reveal today what you chose as the winning message and send that all the way out towards Voyager 1 in interstellar space. This is Jeff Berner, and he is the DSN Chief Engineer. Hi, Jeff.
Hi, Tracy. How are you doing?
I'm doing great, thanks. So can you tell us what's going to be done with the message today?
Okay, well, the selected message is 56 characters long, which translates into 448 bits. And we put it into a Voyager command message format and sending it at the Voyager rate of 16 bits per second, which means it'll take 28 seconds for the message to be totally transmitted. Once it's transmitted, it'll take about a little over 19¼ hours for it to pass by Voyager on its way to interstellar space, it will have traveled 12.9 billion miles.
Okay, and just how is it going to be sent?
Okay, so we are transmitting from the 70-meter antenna outside of Madrid, Spain, which we call Deep Space Station 63. And to give you an idea how big this antenna is, the 70 meters is about 3/4 the length of a football field.
That's pretty fantastic. Well, thank you, Jeff.
Thank you.
I was only 2 years old when the Voyagers launched, but by the time I got to elementary school, we had already started getting back images of Jupiter and Saturn that were really fantastic and helped inspire me to be interested in space exploration and growing up to be an engineer. My mom was also very interested in science fiction, especially Star Trek. I've been a Trekkie since just about I can remember, and I loved how at the end of Voyager the motion picture, Voyager, the alien spacecraft, turned out to be a long-lost Voyager series probe. So who better to help us send today's message to Voyager than Captain Kirk? That's right, William Shatner is with us in Mission Control today.
What an honor. I'm so pleased to be here. It's a magical place, JPL, and this is a magical moment to send a message to Voyager. And once it reaches Voyager, it keeps going. So it's like an advance man. Voyager coming, you know, to all the little green people out there.
That's right. It's pretty exciting. Can't wait to see, or hear maybe in some years from here, if anybody says hello back to us.
Wouldn't that be something?
It would be amazing.
Yeah.
So also here with us today is DSN Command Engineer Annabelle Kennedy, and she's going to be ready to send the message on your command.
She's going to press the button.
That's right.
Yeah.
That's what's going to happen.
So this message was composed by some individual that was chosen by committee once all the attempts to show us, to give us a message. There was 30,000 or something like that?
That's right. 30,000 people submitted
30,000 people communicated, and this was winnowed down to 10, and now one of the 10 has been chosen, and you're going to give me the envelope.
That's right.
And I've done this on award shows. The envelope, please, and we read the message.
That's exactly right.
And Annabelle will press the button, and the message will go out to Voyager to get there 19-something hours late.
It's a long way away.
Yeah.
Are we ready to reveal the message?
Oh, I am so excited. I wonder what they wanted us to say.
I wonder too.
In only less than 60 characters. That's a half a tweet.
That's right. It's not a lot of space in order to put in a really uplifting
Not a lot
message.
of space for a large space.
Perfect. Yeah. Can we have the envelope, please?
Can we have the envelope,
Can we have
please?
the envelope, please? Here we go.
All right. So now I'm going to open it up. And Oliver Jenkins is the message that's been selected. And this is, Annabelle, this is the message. Am I going to read it out?
Yeah, let's have you read it.
We offer friendship across the stars. You are not alone.
That's fantastic.
What a great message. by Oliver Jenkins.
I love that.
Are you going to send it out now?
I am ready to send it.
Are the hailing frequencies open?
They are ready and set
I
to
thought
go.
I'd toss that in for the Trekkies.
Okay.
Command Engineer Annabelle Kennedy, send the message.
On your command. And we are active on 3, 2, 1, active, and we are radiating message to Voyager at 1720:01.
That's fantastic.
I am so delighted.
Me too.
I mean, when you think of the mysterious void that's out there and what little we know, and we're sending a message out and it goes into the stars. It goes, we don't know how long that'll take. How long will that take? No, I don't mean how long. I mean, this electrical impulse
Traveling at the speed of light.
Traveling at the speed of light goes, does it ever decay?
It will spread out eventually over many, 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 many light years.
Yes.
But eventually, if there's something out there with a big enough antenna that can listen, who knows?
Yeah, out there you don't need big antennas. They have little time. So it spreads out and goes forever.
It just goes forever.
Because it's a light, it's a photon.
It's radio signals that are going out, electromagnetic frequencies, yeah.
Right. But it's not a photon.
It's not a photon. Okay.
I am so happy.
Me
Thank
too.
you so much.
Thank you very much for being with us.
Oh, are you kidding?
And we're going to pass it back out to Matthew in Washington, D.C.
So we're back at the National Air and Space Museum here on the Smithsonian grounds of the National Mall, and we have our second panel. We have two new folks joining the panel. I won't reintroduce the folks you already know, but we have Dr. Morgan Cable. Dr. Cable is a research scientist at the NASA Jet Propulsion Laboratory in Pasadena, California. She earned her PhD in chemistry from Caltech in 2010, studying life in extreme environments. Currently, Dr. Cable is Assistant Project Systems Engineer for the Cassini mission, which has been exploring the Saturn system now for 13 years. And she's also a collaborator on the Mapping Imaging Spectrometer for Europa, an instrument selected for NASA's next mission to Jupiter's icy moon. And Dr. Eric Zernstein is an associate research scholar in the Department of Astrophysical Sciences at Princeton University, where he specializes in the simulation and analysis of physical processes related to the solar wind and its interaction with the interstellar medium. He received his BS, MS, and PhD in physics at the University of Alabama in Huntsville, and he's published peer-reviewed articles interpreting observations made by the NASA missions Voyager, Interstellar Boundary Explorer, and New Horizons. So a couple of very accomplished young scientists. So let me start by asking Dr. Cable a few questions. How has Voyager influenced your career as a scientist?
Well, Voyager has had an immense impact, I think, on all of the careers of scientists and engineers of my generation. For me personally, it's been more an impact that the people have made. Being able to work at JPL and Caltech alongside people like Ed Stone, hi, has been amazing. Dr. Linda Spilker, who's the project scientist for the Cassini mission, has taken me under her wing, and through her mentorship, I've really been able to excel with this knowledge passed down from these Voyager veterans. It's really been an incredible way to start to find my own path as a scientist in planetary science and space exploration.
And which planets have you studied that Voyager explored?
Planets, I'm going to say moons are more exciting for me. So I'm really interested in astrobiology. And thanks to the amazing discoveries of Voyager and then building on those with Cassini and hopefully future spacecraft, I'm really excited about a lot of these ocean worlds, these places like Europa around Jupiter or Enceladus and Titan around Saturn, places that have liquid water oceans underneath icy crusts. They seem to have all the ingredients, at least that we know of, for life to survive: water, chemistry, and energy. And here, if we can show, this is an image that Voyager took of Enceladus. This is one of those ocean worlds in orbit around Saturn. Back when Voyager 2, right? Ed was doing its flyby, yes. we captured this amazing image, and you can see that this is one of the whitest and brightest moons in the solar system. Now, unfortunately, Voyager 2's SCAM platform jammed, so it was not able to, at that time, get an image of Enceladus as it was leaving, sort of passing by Saturn. If it had, it might have captured an image of the plume that now we know is emanating out of the South Pole. If we go to the next slide, you'll see this is an image that was captured by Cassini, which was the follow-on mission that is still, at least for the next 10 days, in the Saturn system. I encourage you all, September 15th, early in the morning, to watch the final grand finale of that mission. Captured this amazing image, and the next slide, this is what Voyager 2 would have seen had that SCAN platform been working. This is some material that's coming out of these 4 giant tiger stripes in the south polar terrain of Enceladus. This is free ocean water spewing into space. And thanks to Voyager, we know about these amazing worlds. Missions like Cassini and hopefully some future spacecraft are building on that knowledge, and it's just such a fun time to be a planetary scientist.
So we can better understand this, is there anything on Earth that you could compare these to?
Let's see, the best comparison I think for these types of plume emanations would be maybe a geyser, like Geysir in Iceland or something like that, but the scale is very, very different. Those geysers maybe spray, a few tens of meters at most into the air, but these plumes that are emanating from Enceladus, many jets forming a single plume, spew out at least 50 miles and really more. They form that E-ring that's around Saturn. One of the rings is being formed because of this material coming out of Enceladus.
So what are your plans for the future? What do you want to explore next?
Oh, all the things. I want to explore everything, but Enceladus is top of the list. I would say Europa as well. NASA is currently working on a mission called the Europa Clipper mission that I'm lucky enough to be a part of. We also have a few more in the works. There's this proposed Europa lander concept that we're really hoping will move forward. And then looking further out, these fascinating places like Triton around Neptune. It's orbiting backwards. It's spewing volcanoes of nitrogen and methane and amazing stuff into space. There's so much to explore.
Great. Well, Dr. Zernstein, how did you first get involved in heliosphere research?
I'd have to say it started when I was an undergraduate at my university. I was taking a computer physics programming class, and our professor came in one day and showed us these new observations that the Interstellar Boundary Explorer was just taking. The Interstellar Boundary Explorer is, or short for IBEX, is an Earth-orbiting spacecraft that detects neutral atoms that are created in the outer heliosphere. So these neutral atoms are created at distances where Voyager spacecraft are, and they travel through space and can be detected at Earth. So our professor showed us these observations, said, these are really exciting, but totally unexpected. And we have a brief animation we can show. So IBEX takes what we call a sky map, so a total picture of the sky within 6 months. And what it does is, you can see on the sky map, there's the pixels for Voyager 1, V1, and Voyager 2 on the bottom. These are where they're going away from the sun, away from the Earth. And in the background is what IBEX sees. It sees all these neutral atoms from every direction in space, but what was totally unexpected is this band going across the middle of the sky that we call the IBEX ribbon. And this had essentially excited everyone that was working on it, and I decided to do my undergraduate project with him on it, and it's been like that ever since.
Wow. Well, we see Voyager 1 and Voyager 2 in your graphic. How has your work intersected with the Voyager exploration?
Well, Voyager gives the ground truth to what we heliosphere physicists see in IBEX observations. So IBEX gives a global picture, but Voyager actually tells us what's actually happening in location in space. So using them simultaneously is really important for our research. So ever since it was officially confirmed that Voyager 1 had crossed the heliopause, those unexpected, strange magnetic field observations were maybe not actually that strange after all. So this graphic we're showing, if you first imagine the solar wind coming out from the sun, it goes and just comes out radially from the sun and fills a bubble in space called the heliopause. It's sort of like a comet shape. So this light blue surface is the surface of that bubble, and then outside of it is interstellar space. And you can see the top arrow is where Voyager 1 is outside the heliopause. It's still pretty close on these scales. And the bottom black arrow is Voyager 2, but it's still inside, so there's no picture. And what we can see in this simulation is that the magnetic field lines, which are those black curves snaking from the top left to the bottom right, are showing us how the magnetic field is wrapping around this heliopause surface. And we believe that what Voyager is telling us is how these magnetic field lines are draping around the heliosphere. And as it propagates farther away from the sun, it's going to tell us more about how far this interaction goes.
And what about your plans for the future? What do you hope to see in the future of interstellar exploration?
Well, we can continue to see more observations from Voyager 1 as it goes at, 38,000 miles per hour. And it's going to provide us with more and more important observations for at least the next 10 years. And, but our community, we're definitely expecting Voyager 2 is going to cross the heliopause down at the bottom there. And we believe it's going to be in the next few years, but we're just going to have to wait and see. But what Voyager has shown us is not only is it exciting and astounding to see all these observations, but it's definitely capable. We're definitely capable of doing this, and hopefully it's going to be one of many in the future.
Great, fantastic. So now I think we have some time for some audience questions, and I think we also have a social media question. If anyone from the audience has a question, you can make your way over to the microphone in this aisle over here.
Hello, this is really an inspiring day. Thank you for this, and thank you guys for all you've done. I've always been curious as a space buff since childhood, when my dad took me to see Saturn. When we send out these inspirational messages in the record and so on, as slim as the chance is that they'll be found, was there ever any concern that they might not be nice green people who find it?
Great fear about the nature of the extraterrestrials. Someone as brilliant and illustrious as Stephen Hawking has expressed a kind of sense like, don't let them know we're here. But it's too late for that because of our radio signals as described earlier. We've been broadcasting for something on the order of a century, and the word is out that we're here. What I find so puzzling is that, and maybe just because I've been so lucky to have such a really wonderful life, is that we always assume that the extraterrestrials will have to be technologically much more advanced than we are, because after all, they're spacefaring they're sufficiently good at it that they can flag down a derelict spacecraft in the middle of nowhere. So they're technologically advanced. But we always assume that they will be just as emotionally and spiritually stunted as we are, so that they will treat us the way we treat the rest of life on this planet, the way we treat each other. And I say, beautiful until proven ugly. Let's really, it just makes no sense to me that you could be that good at traveling in space, mastering the planetary quarantine that we're born into, figuring out all of the difficulties and challenges of actually being a spacefaring civilization, and still be out there hunting for lunch or for, something to wear. It just doesn't strike me as practical. And so I say, the Voyagers are literally, as they've often been called, they are messages cast in a bottle in the great ocean of space. They move so slowly that, our radio signals outrun them at the speed of light while they plod along at maximum 40,000 miles an hour. So not to worry.
Yes.
Dr. Stone, I was involved in the flyby of Neptune, and when we went by Triton, you could see those dark clouds or fumaroles. There was speculation they were hydrocarbons, at a very low temperature. Did that ever prove out, or was it something else?
You know?
I know a little bit about that. So Triton's surface is mostly nitrogen and methane ice. And so what happens is as Triton moves through the seasons, you have it's methane snow, right, that moves and condenses. So it moves from pole to pole. And when some hydrocarbons like methane or nitrogen get trapped underneath some of the snow and it starts to warm up, it turns to a gas and it starts to vent out. And that's what you're seeing. And I believe the dark marks are very similar to the tholin, another material that we see on Titan, which is when methane and some other small molecules interact with UV radiation and some other energetic sources in our solar system, it forms larger molecules that are darker in color. Tholin was actually coined by Carl Sagan from the Greek term tholos, which means muddy, because they're sort of muddy colored, right?
Yes, sir.
Get a gold star.
We have a social media question.
Hi, Emily Farfara from NASA Social Media. This question comes from Twitter, and they're asking, when is the next opportunity for a mission that could fly by or orbit Neptune or Uranus?
Try that one. Since it takes a long time with chemical propulsion, we would have to use gravity assist. So I think there are hundreds of possibilities within the next 10 years or so to do that. Can be done.
Yeah, at least a Uranus orbiter has been included in the most recent NASA decadal survey. So there are a lot of ice giant scientists that are huge proponents, as I'm sure we all are, of exploring these fantastic systems.
Another audience question.
Hi, Alice McGraw from the National Academies and Lunar and Planetary Lab. I've got a question about the spacecraft itself and debris. I know that you're measuring plasma, but what about dust? And do you expect it to be a Swiss cheese at this point, structurally?
It turns out that the space is really empty, and the gold cover you see there in the image is, in fact, a dust cover. That's not the record. The record is behind it. That cover is thick enough. It's there because micrometeorites in space would, in fact, disrupt and pit the grooves in the record, but they believe that just that thin plate which is there is more than enough to give a billion-year lifetime against this kind of dust damage. So it's very unlikely. These are tiny micrometeorites.
Could I add one thing?
Yes.
At the beginning of this whole thing, when we were first proposing this, everybody told me that you're wasting your time. You cannot get through the asteroid belt with that spacecraft. You just forget it. You're not going to make it through. But I don't think there was ever any sign of any problem going through.
Hello. With advances in information storage and the ability to crowdsource like we did for the message to the Voyager today, how do you think the process of making another project like the Golden Record would be, and how different do you think the end result would be?
Well, first of all, yes, the opportunity to compress so much. I mean, really, with our nanotechnologies and our abilities to compress, we could send the entire internet on the next really epic mission. We could send the whole, warts and all, everything we are, without any difficulty. It was a challenge in 1977 to select the amount, the pieces of music. The winnowing process was heartbreaking at times for the images, for the sounds, for the music, for the greetings, precisely because of the finite space available on a phonograph record. Still, it made the most sense at the time to maximize the amount of information we could send. But if we were going to send it now, there's a project that I have a peripheral association with, Breakthrough, which is contemplating, it's called Breakthrough Starshot, contemplating sending nanocraft, each craft, a flotilla of 1,000 craft, each craft the size of a lentil with greater capabilities than each of the Voyager. And a tiny little light sail moving not 40,000 miles an hour, but ultimately, if it's successful, a significant fraction of the speed of light. So the possibilities are virtually infinite if we just get our act together here on Earth.
All right. I believe we have time for 2 more questions.
I certainly have enjoyed listening to all of you, young and old, and to see that Voyager has a future. But there's something going around on the internet that I hope maybe you can all, somebody can describe. And that is the effect that Pioneer and Voyager had on getting rid of Planet X.
Well, I think the Pioneer 10, they tracked the spacecraft very accurately, and they thought that they had found a small residual acceleration that was not accounted for by known physics. And that would be very exciting if there was new physics was affecting gravity on a larger scale. It turns out they've reanalyzed the data, and they've analyzed more of it, and they've analyzed it for both Pioneer 10 and 11, and have concluded, unfortunately, it was really material properties having to do with the spacecraft radiating the heat away from the sun. And there is no evidence that there's new physics involved.
Sorry. First, I want to thank NASA for ruining my 7th birthday, because you threw the first one up 5 days before. When everybody started remembering, then you threw another one right up behind it. So, anyway, what I would like to know is like the most white knuckle or scariest moment during the mission process.
Clearly, the scariest time was on Voyager 2 when we lost one receiver and found that the backup receiver no longer could tune to the frequency we were sending. So we had to learn how to send the right frequency so the spacecraft could, fortunately we learned how to do that. But that was a very scary period of several months while we sorted out what happened and what the workaround was. But we've flown the entire mission now with this kind of tone-deaf receiver. And so that's fine. There are many such things that happen on real missions. And normally you don't hear about them because once they get fixed, it's sort of old news. So we're very lucky that there's been no catastrophic failure on either spacecraft yet, but you know that's just the risk of space. I mean, things do happen that you can't fix.
I want to thank our second panel for doing a wonderful job and really giving us some great history and future of the Voyager project. And I want to turn things over to Ann Druyan, who is going to present the final part of our day's activities.
Well, what you see before you up on the screen is Voyager's final look homeward, a picture that was taken because Carl Sagan lobbied endlessly to have it taken. There was reluctance to take it because to look homeward was to look back to the sun, which meant the possibility that the lenses would burn out. But as Carl kept pointing out, well, we're not going to take any more pictures. And he knew that it would be important for us to see our home planet not as the frame-filling Apollo image, which was such a sea change in the history of our civilization. I remember seeing the Earth from space for the first time and seeing it fill the frame and believing for the first time in a kind of visceral way, yes, we live on a world that moves through space. But this is what we really need to take to our hearts right this moment, because that's not the frame-filling center of the universe image of the Earth, but our true circumstances. We live on a 1-pixel world in the scale of the solar system. Forget about the scale of the galaxy. Forget about the scale of the 100 billion galaxies. Forget about part of the universe that we have yet to apprehend. We only understand and really know such a small part of it. And that's really us, as Carl wrote so beautifully. And I'm so glad that NASA acceded to Carl's wishes and took that picture. You know, in the Bible it says you should have it
for a frontlet between thine eyes, and see it as thou walkest by the way in the morning and the night. See that, and teach that to everyone you know, so that we can begin to treat each other the way we should, in a way that would be worthy of our children and grandchildren. Thank you.
Okay. Thank you, Anne, and thank you to all of our panelists and speakers today. On behalf of the Smithsonian National Air and Space Museum, thank you all for joining us as our audience today, and please come and visit us when you can.